Hello students, welcome to my YouTube channel. In this video lecture, I am going to answer questions from sample paper number 1, RK Bali Navigation book. This is the 4th edition book. If you happen to have any other edition book like the 5th, the 6th or the 7th one, no problem. The questions in that book are the same as the questions in this book. So now let's start with question number 41. In my previous lectures, I have solved the first 40 questions. While carrying out a turn at magnetic equator with direct reading compass, there will be no turning error, a tendency to overread the turn through north, underread through south, a tendency to underread all turns due to liquid swirl. So, now your direct reading magnetic compass is subject to two errors: acceleration, acceleration and deceleration errors. And the second type of error is turning error. Okay, turning error. Now, acceleration deceleration error happens at equator, or mainly it happens at east and west headings, at easterly and westerly headings. So when you are, let's say you are flying at a heading of westerly 270, okay, and you accelerate your aircraft, so there will be something called acceleration error. Let's say you are flying 090 heading and you decelerate your aircraft, you slow down your aircraft. So again, there will be a deceleration error. So acceleration deceleration error is happen at easterly and westerly headings. Next, turning error. Turning error happens at north and south headings. North and south heading. So let's say you are in the northern hemisphere, you turn your aircraft to the north direction, that is 350, 360, 010. So when you turn your aircraft to the nearest north pole, there will be some kind of turning error. You are in the northern hemisphere, but you turn your aircraft to the south pole, that is south direction. Let's say from southwest direction to southeast direction, you are turning your aircraft through the south direction. Again, there will be a turning error. So turning error is restricted to north and south headings. Acceleration deceleration errors happen at easterly and westerly headings. Okay. So now here you are carrying out a turn at magnetic equator. Okay, with direct reading compass. Okay, so you are at the magnetic equator here. You are not you're not in the northern hemisphere. You are not in the southern hemisphere. You are midway between both hemisphere at magnetic equator. So if you let's say you are carrying out a turn in the northern hemisphere, so that means you are closer to the north pole than the south pole. If you are carrying out a turn in the southern hemisphere, you will be closer to the south pole than the north pole, right? So, but if you carry out a turn at magnetic equator, you are equidistant from both the poles. So there will be no turning error. So there will be correction. This is the right option. So there will be no turning error at magnetic equator. Next, question number 42. During an IFR flight, task and time appear to deviate from the data in the flight plan. The minimum deviations that should be reported to ATC in order to conform to ICAO rules are what? So, your there are some things that you must report to ATC at all times. One of those things is a deviation of true airspeed and estimated time of arrival, or any estimated time reports from your flight plan. So any deviation in true airspeed during the cruise phase of your flight from the one filed in your flight plan, that must be reported. Any deviation in time uh, that you estimated previously. Let's say in your previous ATC communication, you told ATC that you would end up, or you would reach the next reporting point in 5 minutes, and after reporting that, you found that you are going to reach the next waypoint or the next checkpoint or next intersection not at 5 minutes, but after a delay of 7 minutes, so 3 minutes in excess. So there is a deviation of excess of 3 minutes. Okay, Previously, you told ATC that you would go to that destination or that intersection or that point in 5 minutes, but now you have a revised estimate. You have a new time estimate at your disposal, and you estimate reaching that point not in 5 minutes but next 8-9 minutes. So again, you must report this deviation or this new development to ATC. Now, according to the rules, any deviation of the real true airspeed at which you are flying during the cruise phase of your flight from the true airspeed that you filed in your flight plan must be reported, and that minimum deviation, the minimum limit is 5% of TAS. So, a deviation of 5% of true airspeed that you filed in your flight plan. Let's say you have filed a true airspeed of 400 knots in your flight plan, but the actual speed that you are flying at during the cruise phase of your flight is in excess of 5% of 400, or is less than 400 knots by 5% of it. So you are going to report that development to ATC. And for time, the limit is the minimum deviation limit, which obliges you to report that deviation to ATC is 3 minutes. So correct answer is task 5% deviation, time 3 minutes. Okay. Next. Magnetic heading is 311, drift is 10° left, bearing, relative bearing 270. What is the magnetic bearing of the NDB from aircraft? From aircraft, okay. So first things first, magnetic heading and drift. So with the help of heading and drift, you can obtain a magnetic track, correct? So whenever you have a port drift, with a port drift, heading is going to be more than track. Now here you have a port drift of 10 degrees. Heading is 311. So track will be what? Track will be less than 311. So track will be 311 minus 10, that is 301 degrees. This is your magnetic track. Now, next things. Relative bearing is 270. Magnetic heading is 311. Now, magnetic bearing to the station, nothing but QDM to the NDB station, will be relative bearing plus magnetic heading. So 270 plus 311 is what? 270 plus 311 is 581 minus 360, 221. So QDM to the station or track towards the station is 221 degree. We have been asked to find out magnetic bearing of NDB measured from aircraft. So that means we have to find out QDM. So QDM is 221. Option A is the correct option. So diagrammatically, let's say this is your NDB station. Okay, this is your NDB station. This is your north direction. You are on a track of magnetic track is 301, heading is 311. QDM to the station is 221. QDR will be reciprocal of QDM. So 221 minus 180 is 041. Okay, 041. So you are on a track of 041. So 041 will be something like this. This is track away from the NDB station 041. Track towards the NDB station will be 221. Now your aircraft heading is 311. Aircraft heading is 311. Relative bearing is 270. Relative bearing is measured from the heading of aircraft clockwise towards the magnetic track towards the station. So So clockwise like this. So this is the magnetic track towards the station 221, QDM 221. So this is the diagrammatic representation. Okay. Next. What is the effect on Mach number and TAS in an aircraft that is climbing with constant calibrated airspeed? So you're flying at a constant calibrated airspeed. Let's say this is the atmospheric layer in which you are flying. This is the atmospheric layer in which you are flying. Now in this particular atmospheric layer, what are you going to experience? As you fly at higher altitudes or as you fly from lower altitudes to higher altitudes, atmospheric pressure atmospheric pressure decreases. Atmospheric pressure decreases at higher altitudes, right? Lower altitudes, atmospheric pressure increases. As you descend to lower and lower altitudes, atmospheric pressure is going to increase. Is going to increase. Now, your airspeed indicator is a pressure instrument. Is a pressure instrument, and it requires dynamic pressure. It requires dynamic pressure for it to successfully represent or indicate indicated airspeed to you or calibrated airspeed, right? So dynamic pressure is registered and that information is represented in the form of indicated airspeed, calibrated airspeed in terms of knots. Now, as your aircraft climbs to higher and higher altitudes, atmospheric pressure surrounding it decreases. This decrease in atmospheric pressure will be registered by your airspeed indicator. So decrease in atmospheric pressure means less dynamic pressure will be registered in your airspeed indicator, and this less dynamic pressure that is registered or that is the input, this will be this will translate into your output. So less dynamic pressure will be represented or indicated as less forward speed of your aircraft, means less calibrated airspeed, correct? So less, I'm writing it here, less atmospheric pressure equals to less dynamic pressure. This less dynamic pressure will translate into a lower indication of calibrated airspeed. Lower indication of calibrated airspeed. Your aircraft may still be flying at a constant true airspeed, but the indication shown to you, the calibrated airspeed shown to you will start decreasing in value. Okay. So in order to maintain or in order to prevent that calibrated airspeed from falling or decreasing in value, you will have to compensate for this decrease in atmospheric pressure that you encounter at higher altitudes. So how will you do that? How will you achieve that? So the solution is increase increase the true airspeed increase the true airspeed of your aircraft. Now, when you increase the true airspeed of your aircraft, the forward speed of your aircraft, what will happen at pitot tube of your aircraft? There will be more pressure, more impact pressure around pitot tube. This more impact pressure, this more dynamic pressure will be registered by the ASI, and this more dynamic pressure means or translates into more calibrated airspeed. Okay, so this is how compensation happens. This is how counterbalancing happens. We have less atmospheric pressure surrounding us, natural pressure. So we are going to increase the true airspeed of your aircraft. So that increase in true airspeed will bring more dynamic pressure, impact pressure around the pitot tube, and that will convert or transform into more calibrated airspeed indication, right? So in order to maintain, if you want to maintain a constant airspeed in your airspeed indicator in a climb, okay, in a climb phase of your flight, you have to increase the true airspeed. Without that, if you don't increase true airspeed, you may be flying at a constant true airspeed, but you don't increase it, calibrated airspeed value will start decreasing automatically. So, in order to maintain a constant calibrated airspeed, increase the true airspeed of your aircraft. Increase the true airspeed of your aircraft. Right? So, there are option A says task decreases, which will be wrong. Task remains constant, wrong. Task increases, yes. So option Charlie is the correct option. Now what is Mach number? Mach number is nothing but your true airspeed as a fraction of local speed of sound. So that means Mach number is directly proportional to true airspeed. It's nothing but true airspeed as a fraction of local speed of sound. Okay, with respect to local speed of sound. So if true airspeed increases, also your Mach number will directly increase, directly proportional. So option Charlie is the correct option. 46. In case of accidental closing of aircraft's left static port, the altimeter will do what? It will overread in case of a side slip to the right, overread in case of side slip to the left, display correct information during a symmetric flight. So here you are side slipping to the left and you have left static port locked or closed. So what happens? Your aircraft has two static ports. Let's say this is your aircraft. Okay, this is the nose of your aircraft. This is the tail of your aircraft. Your aircraft will have two static ports on each side of the fuselage, over here and over here. Okay, each side of the fuselage. This is done in order to have the correct input of static pressure towards your altimeter, in your altimeter. Now what happens? Let's say you have only one static port on either side of the fuselage. Let's say you have one static port or only on the left side of your fuselage, not on the right side. So what will happen? When you are flying straight and level, accurate registration of static pressure will happen and this input will be provided to all pressure instruments. But let's say the moment this aircraft starts slipping like this to the left hand side or to the right hand side like this, what will happen? This static port will be like this. This static port will be here like this. So now if you turn left or if you move to the left hand side, the forward air, the relative airflow coming from the front in both cases, right? Right, when you are turning left, the static port will also get deflected to the left or move sideways, right? That means this static port is protected or is hidden from the incoming air relative airflow, oncoming relative airflow. If aircraft moves to the right hand side, the static port will be directly exposed to the oncoming relative airflow. This relative airflow will affect the registration of static pressure. So in a straight and level flight, accurate indication of static pressure will happen because the oncoming relative airflow won't interfere with it. But in case of side slipping, left, right, whatever, the incoming or oncoming airflow will interfere with the static ports. Now in this case, when aircraft is deflected or yaw to the left static port gets hidden from the relative airflow. If it's yaw to the right, the static port gets exposed to the relative airflow. Now in this case, during this left case, if the static port gets hidden from the relative airflow, altimeter will indicate, altimeter will overread. Why overread? Now when the static pressure or static port gets hidden from the oncoming relative airflow, the effect of that is decrease in static pressure, decrease in pressure on the left side of your aircraft and increase in pressure felt on the right side of your aircraft. Why? Because there is relative airflow coming directly from the front. So there will be increased pressure registered on the right side, decreased pressure registered on the left side. So if this static port, which is on the left side, registers a lower static pressure, lower than expected, so that means it will overread. Why will it overread? Because lower static pressures are expected to happen, to exist at higher altitudes, right? So your aircraft may be flying straight at 5,000 feet, tilted left hand side. Okay, it is flying at 5,000 feet, but the static pressure sensed by the static port is lower than the pressure existing at 5,000 feet. Since the pressure registered is lower, the altimeter thinks this lower pressure must be encountered at higher altitudes, or this lower pressure is expected to get encountered at higher altitudes, and therefore this lower static pressure gets transformed into higher indication of altitude. Opposite happens if your aircraft static port is exposed to the wind. When it exposed to the wind, there will be increase in pressure created by this impact of airflow. Increase in pressure near the static port. On the right side, there will be decrease in pressure. Right? There will be decrease in pressure. So as a result of that, the altimeter in this case, the altimeter in this case will underread. Altimeter in this case will underread. Okay. Now to do away with these errors, to do away with this errors, what we have is we have two static ports on each side of the fuselage of aircraft. So even if aircraft tilts left or right hand side, these two static ports tend to cancel out any disturbances or any differences between each other, and accurate static pressure is registered by the altimeter and accurate altitude is indicated. Okay, so this two static ports. So even if one static port gets hidden from the incoming airflow, the second one will be exposed to the relative airflow. So the decrease in pressure here is counterbalanced by increase in pressure on this side. So as a final result, final end product is that we have the same static pressure registered, which is expected to be registered. So this is the advantage. Now in this case, we have a left static port blocked, right? We have two static ports. The left one is blocked. So will the altimeter overread in case of side slip to the right? Overread in case of side slip to the left. So correct answer is option Charlie. Overread in case of side slip to the left. So during a side slip to the left, what like this, the left static port will be exposed to the incoming relative airflow, and this left static port is blocked, and the right static port will be hidden from the incoming relative airflow. Now since this left static port is blocked, it will not register enough static pressure or the accurate static pressure. That means indirectly it will register a lower pressure lower than that expected. So lower pressures translate into higher altitudes. So overread the altitude in case of side slip to the left. And if it's flying symmetrical, straight and level, it will display the correct information. If aircraft is equipped with one altimeter which is compensated for position error and another altimeter which is not, all other factors being equal, at high speed the non-compensated altimeter will indicate a lower altitude. At high speed the non-compensated altimeter will indicate a higher altitude. So option Bravo. So an altimeter which is compensated or which has been accounted for any kind of position error like side slipping, pressure error like turbulence and all that, it will indicate accurate altitudes at all times. But any altimeter which is not accounted for these errors, which doesn't consider these errors like turbulence, prop wash, and the third factor is this side slipping. So this altimeter will be subject to these errors. Okay, and at high speed, now when your aircraft flies at very fast speeds, the pressure around the static port will decrease. Okay, because of this high velocity, and this decrease in static pressure will be registered by your altimeter. And like I said, lower static pressures means higher altitudes, because at high altitudes we get lower atmospheric pressures. So altimeter registers or thinks of these lower static pressures to be higher altitude. So correct option is at high speeds, the non-compensated altimeter, the altimeter which is not corrected for this kind of error, will be subject to this error, and it will show an erroneous information, higher altitude. Next, question 48. After an aircraft has passed through a volcanic cloud which has blocked total pressure probe inlet of ASI, the pilot begins a stabilized descent. It finds that indicated airspeed have what? Now your airspeed indicator is the only instrument which depends on both pitot pressure, pitot pressure and static pressure. The other two pressure instruments, that are altimeter and VSI, these two pressure instruments only require static pressure, but ASI require both pitot pressure and static pressure. Remember that. So pitot pressure uh, enters your ASI through pitot tube, correct? Now if this pitot tube gets blocked due to dirt, dust, ash originating from volcanic eruption, this pitot tube will get completely blocked. That means there is no way pitot pressure can get registered in your ASI indicator. So the only input that is being fed to the ASI indicator, that will be fed to the ASI indicator, will be static pressure, right? We will not have pitot pressure being fed into the ASI indicator. We will have only static pressure, because static ports are operating, but in the question it's given total pressure probe is blocked, but static ports are operating. Okay, so if pitot probe gets blocked, so no pitot pressure, right? No pitot pressure, no dynamic pressure. As a result, the only information entering the ASI case or instrument is static pressure. So ASI will automatically start to behave like an altimeter. Okay, it will only respond to changes in static pressure. So it will behave like an altimeter. So what will happen? When you begin a stabilized descent, that means when you come down to lower and lower altitudes at a constant stable airspeed, your ASI indication will also start decreasing, because it will start behaving like an altimeter. Now think what altimeter will do when you descend. The indications of altitude will start decreasing, 5,000, 4,000, 3,000, 2,000, so decreasing. Similarly, ASI indications, the ASI arrow, the ASI needle will also start showing a decreasing trend. Okay, just like an altimeter. So indicated airspeed of your aircraft will decrease because pitot tube is blocked, static pressure is open, so static port is open, so static pressure is getting inside the ASI instrument, and your ASI behaves like an altimeter. 49. What happens to Mach meter indication in a constant rectified airspeed climb? So like I said, just now we did this question over here. What is the effect on Mach number and TAS when aircraft is climbing with constant CAS? So like I said, when you are climbing at constant calibrated airspeed, what happens? Atmospheric pressure decreases. This decrease in atmospheric pressure is equal to decrease in dynamic pressure, translating into lower calibrated airspeed indication. So to prevent that from happening, we must increase or accelerate true airspeed of your aircraft. So in a constant calibrated airspeed climb, your true airspeed increases, so as the Mach number. So does the Mach number. Now here in this question, again you are in a constant rectified airspeed or calibrated airspeed climb. So your Mach meter indication will increase, because in a constant rectified airspeed climb, TAS increases. As a result, Mach number which is proportional to TAS will also increase. 50. The hysteresis error of an altimeter varies substantially Mainly with what? So correct answer is time passed at a given altitude. Hysteresis error is nothing but lag error. So when you spend a lot of time at a constant altitude, flying straight and level at a given altitude, the aneroid capsules in your aircraft will be subject to lag error. So that means after flying for a long time at a same constant altitude, you tend to change your altitudes, climb or descent. Altimeter will lag behind. That means it will take some time to register the changes in pressure as you climb or descend. And these changes in pressure will be translated into corresponding vertical distances like altitude, height, pressure, altitude, whatever, after a lag of 2 to 3 seconds. So instead of getting shown instantaneous indications, quick indications by altimeter, we get the right indications after a lag of some few seconds. So that is hysteresis error, which is inertia, basically lag error or inertia. Okay. So time passed at a given altitude increases this error. So this concludes our lecture. I hope you have understood all the 10 questions that I did in this video lecture. If you have any doubts, comments, feedback, let me know in the comment box of this video. Best of luck. In my next video lecture, I will be doing the next 10 questions from this sample paper number 1. I request you all to share this channel, this particular video lecture with all your pilot friends. Subscribe if you haven't yet and hit the like button if you have liked this lecture. See you.